Okay, so far in chapter 4, we think back specifically to section 4.1, we had taken a look at antiderivatives, or we've called them now integrals as well, and we looked at them as being sort of reverse of what we would have classified as the simple derivative rules, right? So in particular, we didn't talk a whole lot about what happens with product rules, chain rules, and quotient rules, correct? And the big picture answer to the reason why is because those are really complicated. And they don't have a complete, simple version that says, if you see this, you absolutely are going to do this every time, okay? So we're going to delve into one small aspect of a way that we can work with them that works sometimes, okay? And then the rest of the what do we do if the others don't work, and what do we do if it doesn't work, actually don't show up in this textbook until chapter 8. And if you check in and talk with anybody who's in my Calc 2 class, they will tell you it's complicated, okay? Because that's what we're doing in chapter 8 in Calc 2 right now. They're having a test on it on Thursday. It's complicated and it's very messy. So the nice thing for what we're doing right now is that you don't have a lot of tools. Okay, that's actually a good thing. That means there's not a lot of things you have to try to get to the point of finding out, how do I do this? So far, gateway kind of style stuff, you've had algebra simplification, right? And you've had trig simplification, like trig identities, and that's it. Those are the only tools that you have had in order to be able to find antiderivatives. So in some ways, I'm very limited in what I can ask you. It has to fit into one of those two categories, right? And now we have a third category, and this one's substitution. So I'd like for you to think about what happens when we take the derivative specifically of something. So if we have sine of x cubed minus 4x, what is the derivative here? It's a chain rule, right? So what is the derivative of y equals sine of x cubed minus 4x? Okay, so first it's going to be cosine. So cosine, and then what do we do? All right, we leave the inside the same, and then we need the derivative of the inside, which would be 3x squared minus 4. Okay, everybody good with that? It's a chain rule problem, right? We take the derivative of the outside, that's the derivative of the sine part, leave the inside the same, and then we take the derivative of the inside. And you could switch the order of those two things if you wish. What we're going to be doing in this section is essentially going in reverse. We're going to have something that looks like y prime equals cosine of x cubed minus 4x times 3x squared minus 4. We're going to have something that looks like that, and we're going to try to go backwards and find out that that is the sine of x cubed minus 4x. So the difficulties, if you just started right here, is that it looks like it's a product, correct? It doesn't just look like it is a product. So what difficulties are there in finding y? Well, the difficulty is that it's a product. So when we're working with something that doesn't have algebraic simplification, there's no trig simplification, like those two things that we've done so far are out the window, our only third option is to consider it and to look like, is it a chain rule that I've taken the derivative of? Okay, so if we take a look, this is one option when we're presented with finding an antiderivative that looks like a product, is to decide if there is a composite function meant that we would have had a chain rule, present for which the inside function's derivative is one of the factors being multiplied. So that's what happens over here. The inside function's derivative, right? The inside function's derivative, which is 3x squared minus 4, is one of the pieces that's being multiplied. Okay, that's the description on the next slide. The inside function's derivative is one of the pieces being multiplied. So if and when that's the case, so we can consider y prime above, the x cubed minus 4x is an inside function of a composite function. Its derivative 3x squared minus 4 is one of the factors being multiplied. So here's what we do. We let u be the inside function, and then the derivative of u, which is du dx, would be the 3x squared minus 4x. But more commonly, we will write this like this. du is equal to 3x squared minus 4. Not 4x, sorry, over there. That should have said 4. Apologize. No x here. 3x squared minus 4. And then I have the dx on the other side. So it almost looks like that we're multiplying the dx to the other side. And when we write this, generally, I just start right here. I might start one step earlier just for one example to remind you. And so it ends up looking like this. The integral of the cosine of x cubed minus 4x times 3x squared minus 4 dx has this piece identified as u. Okay, so u is x cubed minus 4x. du, from what we wrote above, is the 3x squared minus 4 dx. So this piece right here gets identified as du. So now we've changed the variables to u, so cosine of u, and then we have du. The antiderivative of cosine is sine, positive sine of u, plus my c. And then I resubstitute the value back in for what it was. U was x cubed plus minus 4x plus my c. And you'll notice this right here was where our original problem started when we took the derivative and we created this process, right? I know there's a plus c. We've already talked about how that works. You can shift it up and down because the derivative of c is going to be 0. But we end back up with the sine of the x cubed minus 4x. So you might feel like as you're looking at this, like, okay, you just created something, you took a derivative, you went backwards, of course you're going to get the same thing, right? But that's kind of the point. I want to show you that it gives you back what we would have had, right? We've talked about the fact that how do I know I took an antiderivative right? Well, I know I did the antiderivative right if I take the derivative and I end up back with what I started with, right? That's how I know. I reverse the process, and that's what's going on here. So we're going to see some pieces, each one along the way, where the inside function, when I set it equal to u, looks like when I take its derivative, I have the other piece. Okay, so taking a look at this, at any given point, you should ask yourselves, can I algebra simplify this, right? Can I do some algebraic simplification? The answer here is no. What is it about this that makes the algebra simplification not possible? Yeah, I've got a cube root, right? If I have a cube root, square root, whatever the radical part is, that radical part means that I can't combine what's underneath the radical with what's outside the radical in a very clean way, right? That's the red flag that says this is an algebra simplification. So if I were to identify an inside function from a composite functions perspective, it would be this piece right here, because it is inside or underneath, it's embedded within the cube root. So over here, we're going to say that the u is equal to 3 minus 4x squared. Okay, is everybody good with that? Okay, this is the only one I'll do this for, but I'm going to write down that this is du dx. Remember, that is one of our notations for derivatives. It's not one we use all that frequently. That's fine. We normally would write u prime. But for the purposes of integration and the pieces we're shifting around, I'm going to write it as du dx. What is the derivative of 3 minus 4x squared? It is negative 8x. Now, I want you to notice it's not negative 8x because there's a negative 8x over here. Yes, there is a negative 8x over here, but that's not why I just got negative 8x. It's because I took the derivative. Are y'all with me? You actually physically have to take the derivative because they won't always match up perfectly. We'll see one shortly that doesn't. All right, this one is matching up perfectly. Yes, there's a negative 8x here and there's a negative 8x over my problem. I get that, but they're not always going to match up perfectly. So this is negative 8x, and then if I rewrite this, this would be that du is equal to negative 8x dx. So we're going to do our substitution step. This is called u substitution because we tend to use u's. Occasionally you'll see another variable used when the u is already in the problem or something, and they might change it to a v. That's kind of our next default. So the piece underneath here is u. This piece over here at the end is the du part. So don't change pieces that don't get changed, right? Like the cube root is still there. It didn't go away. But the thing that's underneath it now is a u. And the piece that's after it is du. And then I can do the things that I've been doing all the way along. Okay, well, this is a power of 1/3, right? Cube root is a power of 1/3. And now it's in a form that I can take the antiderivative of. What is the antiderivative of u to the 1/3?
4/3 over 4/3.
Okay, so I increase the power by 1, so I'd make it a 4/3. I can either write it over 4/3, which is fine, or you can write it as 3/4 at the front, right? Eventually, you're going to get to the fact that it is the 3/4 in the front. We're not going to divide it by a fraction kind of piece and leave it there. I still need a plus c at the end. But the problem started out in terms of x. So the problem's answer also needs to be in terms of x, or whatever variable you started with, okay? So I need to change that u back into what u is equal to. So u is equal to 3 minus 4x squared. And this says power of 4/3. I'll do this at the same time. Power of 4/3 means this whole thing has a power of 4, and it's underneath a cube root. I've run myself out of space. Let me shift this over. Plus c. And again, the reason I put it back in radical form is because it started in radical form. This is not the only answer that you could see happen. I'm going to mention another version, but this one right here is perfectly fine for you to stop at, okay? But you could also see if you were like checking your answer with something, or if WebAssign's doing things where you're like, I don't know how they got to there. I want to show you a little bit of algebra that can change this around and still be equal to what it was before. So I could recognize that this is a cube root of a power 4. So if I had, I'll do it simplifying with the u first. So this is u to the 4/3, right? U to the 4/3 is the same as u to the 1 and 1/3. Right, that's what 4/3 is, right? Everybody good with that? So I could represent this as u to the 1 and u to the 1/3. So the u here, I have a 3/4 in front. My u is 3 minus 4x squared. That's the u to the 1. And then the 1/3 would be the cube root of the remaining 3 minus 4x squared. Now, that's not simpler than what we had. I'm not advocating for you to change it at all. But I do want you to see that there is another version, and this one doesn't necessarily need to be here, but that is where it's coming from. So in some sense, you're taking out one of these u's, right? U to the 4/3 is a u, and a u to the 1/3. The u is the 3 minus 4x squared here, and then the 1/3 part is the cube root part at the end. So that is another way that you can see it written, but I am so perfectly happy with this being our answer and us stopping here as well, okay? All right, are we good? Okay, let's try another one. So again, on this one, there's no algebra simplification that's going to help us here. Can you see what I would want to define as my inside function, as my u? Yeah, the 1 plus x to the 4th. So while it's not always the case, often, remember, inside functions are the parts that are inside a parenthesis, or they would have to be inside a parenthesis if you put it into your calculator. So it's a good place to start looking for what is my u. It's going to be the part that's inside, typically inside of a parenthesis or something like that, which this one is. So this is 1 plus x to the 4th. Now, I'm going to write this just as du this time, and I'm going to put my dx on the end. What is the derivative of 1 plus x to the 4th? 4x to the 3rd. Now, please notice, I do not have 4x to the 3rd in my problem. But what do I have? I have the x to the 3rd. And that's the important part. Constants are easy to manipulate and fix, but the variable part has to match. So I have an x cubed in my problem, right? It's on the numerator, which is where I need it to be. And I have x cubed as part of my derivative that I just found for du, right? So what do I do with the 4? Well, I just divide it to the other side. So in some sense, we can think about this as 1/4 du is equal to the x cubed dx. So over here in the original problem, this piece is what I identified as u. And this piece right here is 1/4 and du. Is that okay? Everybody see the pieces that I changed around and where they came from? All right, so I'm going to write one step where I replace them. So I'm going to put the 1/4 at the top and I'm going to put the du at the back. I don't particularly like the fraction on top. We'll fix that in a minute. And then this is u, and it has a power of 2, right? I've kind of covered it up at this point. Let me kind of uncover it. There's a 2 power right there that I still have to have on that denominator. Now, it does not look especially pretty to have a 1/4 on top of a fraction. And so I am far more inclined, personally, to put the 1/4 at the beginning and to leave it as a 1 on the top. Actually, let me go ahead and write that for a moment. If you can jump straight to the 1/4 in the front, that's great. If you want to see the 1/4 on top and then move to the front, that's fine too. If you want to leave the 1/4 on top, that won't hurt anything and it'll be okay there as well. Okay, so lots of options. But if I'm going to work with this and find the antiderivative, it would be far friendlier to at least write this as u to the -2. Alrighty then, so 1/4 as a constant multiplier, whether it's on top or whether it's at the front, comes along for the ride. What is the antiderivative of u to the -2? Fantastic. With my plus c at the end, right? Thank you, Kate. Sorry. Okay, is everybody good with that? Okay, so let's manipulate it a little bit with the u's before we go putting the x's back in. I'd like to move the negative out here with my 1/4. And that u to the -1 will go back into the denominator as just simply u. So it would look like that as a simplified version with u's in it. And then I need to replace the u with what u is actually equal to, which is x cubed. That's not true, sorry. I wrote that wrong. I get my u, not my u du. My 1 plus x to the 4th. There we go. There we go. And then plus c at the end. If you want to distribute the 4 through, fabulous. If you leave it in the front, that's fine too. There's sort of benefits to either one depending on if the problem continues or you do anything next. Neither one's really any better than the other. So this is a perfectly reasonable place for us to stop. Okay, it does matter that the u is in the denominator, right? That the 1 plus x to the 4th does not have a negative exponent because it didn't start with negative exponents. So we want to make sure it doesn't end with them. And we definitely want to make sure it ends with x's in the problem because that's how it began and not with u's as the ending place. Okay, any questions on that one? Okay, let's try one with a little bit of trig. Okay, you do not have any trig simplification that will help with this. No trig identities will help you with this. And it does look like a product, right? So what does it mean for it to be a product? Sometimes we get confused with this. Products mean you have two pieces that both have x and then they're being multiplied. Okay, so just because there's multiplication does not make it a product. It's because both of the pieces of what you maybe think is of as a product have a variable component, and these do. And so did the last two that we have done, okay? So as you take a look at this, there's no parentheses here. I saw parentheses in the last problem, right? I had a radical on the first problem. So I don't have parentheses to go to, but you should be able to identify what your inside function is nonetheless. What would your inside function be? X to the 4th. And again, while they're not there, if you put this into your calculator would probably force there to be parentheses here, right? So it's another way to sort of try to identify is like, if I were to put this in something else, where would the natural parentheses exist? And they would exist around the x to the fourth. All right, now what is your du? 4x to the third, and we put the dx as the ending point over here. Now this one's nicer than the last one because it's actually right there, isn't it? Now it's at the beginning, but that doesn't matter. This piece here is u, and this piece are my du. And so I make a substitution step. Integral at the beginning. The 4x cubed and the dx at the end are my du, and I put it at the end. It's sort of a bookend to the script S, right? I still have sine. Don't lose the sign. And it's the sine of u. So what is the antiderivative of the sine of u? It is negative cosine of u. We'll add our plus c. Am I done? Yeah, I need to replace the u. So I will replace u with what I set u equal to at the beginning, which was x to the fourth plus c. Okay, how can I make sure I did it right? You just take the derivative. Yeah, you're on the right track. You just take the derivative. If I were to take the derivative of this, right, this would imply that I would need to use the chain rule. Agreed? I'd take the derivative of the outside piece. The derivative of cosine is negative sine, so this negative would cancel out, giving me the sine that's back there. The inside would stay the same as x to the fourth. And then the derivative of x to the fourth would be the 4x cubed that's over here. Okay, so you should be able to eyeball this and say, if I actually take this derivative, will I be back where I started? And if you are, then you've done the process in the right way. Okay? Okay, let's try another one that's a little bit less obvious on the inside and the outside. First of all, you might look at this and say, Dr. Hans, that does not look like a product. And you're right, it doesn't. Could we change it so that it looks like a product? Sure. And in fact, it might be helpful. Go ahead, Caleb. How could I change this? Okay, so the sine of x would stay put, and then I would write the cosine of x to the power of negative 3. And in fact, if I do that step, it sort of starts to seem pretty clear as to what my u would need to be, right? It does. It's easier to see here than it was originally. What would my u need to be for this problem? Cosine of x. Right, it's in parentheses. It's raised to the power of negative 3. Now, it's still to the power of positive 3 in the denominator, so if you thought of it from that perspective, that's not a problem, but eventually you're going to have to move it up anyway to take the antiderivative, so the beginning is a good place to do that. What's the derivative of cosine of x? Close. Negative sine of x. Those signs will catch us, don't they? They catch us. Now, I don't have negative sine x in my problem. What do I have? I have positive. So I will simply divide both sides by negative 1, which is in essence moving the negative to the other side for my replacement. So when I replace the sine of x and the dx here, they will get replaced by a negative and a du. And then this piece right here is my u. So I'm going to put my negative at the beginning and my du at the end. What will go in between? Good. U to the power negative 3. Exactly. Does everybody see how we got there? Good. Okay, so negative is part of my answer from the outside. What's the antiderivative of u to the negative 3? Yeah, u to the negative 2. Over negative 2. And the negatives will cancel, you're right. All right, so I have the 2 in the denominator, but it's now positive. The u to the negative 2 can move back to the denominator as well and be u squared, right? I'll have a 1 on top and a plus c at the end. What's my last step?
Plug in.
Yeah, replace it. Now, you can write this one of two ways. If you want to write this as cosine of x squared like that, that's totally fine. Or if you want, you can write it back sort of with the 2 in between. So you can write cosine of 2 right there as a cosine squared like that with the 1 at the end. With the 1 on top and then the plus c at the end. Either of those are perfectly fine. The second one just eliminates the need for the parentheses. Okay. Let's shift gears a little bit. Let's look at number 5. Number 5 wants us to actually find an equation that satisfies some conditions. We talked about this back in section 1, I think it was, in 4.1. So if we're finding a equation for f of x when we're given f prime, we're asked to find the antiderivative, and then we're going to evaluate at some points when we're done to find the plus c value. So we're going to take the antiderivative of secant squared of 2x, right? That's what we're going to be doing. So do you see an inside function here?
Yeah,
Yes. Now, it's not a very exciting inside function, admittedly, but there is one. And you might be saying, yeah, but there wasn't a product present here. And that's true. It does not look like there's a product. But the reason is because the inside function is not very exciting. What is the inside function? 2x. And what's its derivative? 2. It's a constant, right? The derivative of the inside function is a constant. And we talked about the fact that constants are easy to manipulate. All I have to do to shift this is to divide it to the other side. So while I don't have a 2 in my problem, I now will have a 1/2. So I do have a replacement. I do have a u substitution. It's just not a real exciting one. I have the 1/2 and the du on the end that are replacing my dx. I still have the secant squared, but now it's the secant squared of u. You know the antiderivative of secant squared of u. What is it? Maybe you don't.
Is it secant times tangent?
Nope.
Wait. Oh, it's tangent squared.
Close.
Or just tangent?
It's just tangent. The derivative of tangent is secant squared. So the antiderivative of secant squared is tangent. And then I will replace the u back in as 2x. Now what I have found is f of x. But what it wants me to find is it wants me to find what c is. And it gives me an extra bit of information in order to be able to do that. It tells me an ordered pair that this goes through. So remember what the plus c does. The plus c says I can shift this up and down. The image is the same shape, it's just shifted. So if I isolate a location that it actually has to go through, I remove the ability to move the shift, right? There's not going to be an ability to do a plus c on the end. And I can find that c value by evaluating it in for these points. So here, x value is pi over 2. And all of this, right, when I put the pi over 2 in, is going to equal the y value of 2. So 1/2 tangent of 2 pi times 2, 2 pi divided by 2, the 2's would cancel. So I now have 1/2 tangent of pi plus c is equal to 2. What is what is the tangent of pi? Do you know?
0.
It's 0, yeah. The tangent of pi is 0, so this is 1/2 times 0 plus c, or just 0 plus c, which tells you that the c value is equal to 2, right? So we found out that c is equal to 2, so our f of x function is 1/2 tangent of 2x plus 2. Okay, so we have 3 examples left. I knew that that might happen because I knew we had the quiz this morning that was going to take us, 15 to 20 minutes, which is what it took. So when we come back next time, I will do the last 3 examples. I will postpone this homework to be due on Monday. If you wait until Sunday night to do this homework while you're preparing for your exam, don't expect the exam to go so well because you're still learning new material, okay? So you will be very clear when you come to a point between now and Friday when you can't quite finish what you have learned so far. Like there's a point when you're like, this doesn't look like anything we did, okay? I would strongly encourage you to get to that point on the homework so that you're not trying to scramble and do everything this weekend. Make sense? All right.